don't know.
Uh, can you hear me, Alex? Not able to hear. Perhaps my internet isn't working. How much more time do we need? Can you chat in the Join Me group or in that box there and just tell me how much more time you'll need? Is there any? 2 more minutes. Okay, thanks. 3 or 4 minutes. Okay. You guys are in the same group. That's not good. Okay, what about some of the other groups? How much time do you need? Drew, I'm not sure if you can hear me. Drew, can you hear me? Or Hammer?
I
Okay,
can hear
Drew,
you.
this is actually electricity and magnetism right now. Your class is actually going to be around noon. You're welcome to kind of hang out and see what we're doing, though.
Okay.
You could stay. Did you hear me?
Yep.
Okay. Could you? Okay. Yes, Mark, I will try to get over there and help you out. Anybody kind of wondering what's going on up now, so so just kind of be patient for a second. Okay, can you guys hear me? Okay, so I think maybe I've probably given you enough time now. So is it possible we could have a volunteer to kind of present their board, and I'll just transfer over control to you guys? Volunteers. You. Let's see if I can remember how to do this. Let's see here.
Bart's can just request control and then you can hit yes.
All right. All right, perfect.
Okay,
So I'm not sure. Yeah, we can. Perfect.
Okay, excellent. Can you see this?
Yep, we can see it.
All right. Well, so the first thing we did is that the electric field lines represent the movement of what a positive test charge would be, that both lines would be going the same direction, since it repels from the positive on this side and attracts towards the negative on this side.
Okay. And so you found those two and you calculated them.
Added them up, and we got 7.763 times 10 to the 7th newtons per coulomb left.
Okay. Any questions? Okay. You want to transfer it back over to me, Michael?
If I can figure out how, yeah.
Let's see. Maybe I could do it. I'm not sure.
Wait,
Here we go. Okay.
did that do it?
Okay, I got it. Sorry. Any questions on that one? Yes.
Can you hear me?
Yep.
All right. So I asked you earlier if you could just use KQ net over R squared, and I think that does work, doesn't it?
Okay, so you say KQ net over R squared.
Yeah, rather than finding the two fields and subtracting them, can't you just
I guess that would work. I guess that would work because you can factor out the K and you can factor out the R squared, and so you are just summing that up. However, I would caution you because you really need to draw those vectors to see if you are in fact finding the net, and you'll see what I'm talking about.
No, I know what you mean. I was thinking about that when I did mine.
Right. For instance, this next one, we're getting ready to do part B. And if you do it the same way where you do the Q net, you'll get the exact same answer, right?
Yeah.
Yeah, but it's not going to be. And that's why drawing those vectors are pretty important. So,
oh, no, I got a different answer. Yeah, I added them, I think, or...
Okay. But do you see why Do you see why I said no originally? Because it's not always going to be adding those charges up.
Right, I see what you're saying.
Okay.
Actually, I got the same answer using an imaginary test charge in the middle.
Yes, and you would, Michael. That's exactly right. Because you probably found the forces first, right?
Yeah, and then those were in terms of just the generic Q, and since
Right.
C equals QE, the Q went away from both sides.
That's right.
Right,
Yes.
that's kind of what I was thinking.
Yes. Yeah, you can do that. You can find the net force first and then find the E field. That's kind of what you're doing there. That's because the E field is defined in terms of the force. I guess I wasn't totally understanding what you're doing there with that, Michael. I thought you were wanting to know whether you needed to know a charge in order to solve the problem, and you don't. And so you understood that, and yes, you can go ahead and solve it then.
All right.
Okay, so let's go ahead and do part B then. So go ahead and jump back in your groups and do part B. How much more time do you guys need to finish your whiteboarding problem, E&M students? Okay. Okay, so everybody's good? Anybody needing help or anything? Okay, so can I have a volunteer? Don't all jump up at once. The quicker somebody volunteers, the quicker we can move on. All right, okay. Mike, I'm going to go ahead and see if I can transfer it over to you. Well, let's see. Let's see, Mike, where you at here? Why am I not seeing you on here, Mike?
I'll just request control.
That works. Okay, perfect.
All right, can you guys see my screen well now?
Yep.
All right. So when both charges are positive, the fields are opposing each other, so you have to subtract them to get the net. That's what we did here.
Okay. So you use the same E-fields, but you subtracted them.
Yeah.
Okay, and it points to the right, it looks like. So you could have used your idea of, you know, figuring out the total altogether in just one, but what would you use for the Q net in that case?
Q net would be I think that would be if you subtract them, it'd be like 2.2 microcoulombs.
Okay, right, right. So as long as you understand you got to draw those vectors first to see what's going on, then I think you'd be fine.
Yeah, that's what I did.
Okay, good. Any questions from anybody? No questions? Okay, Mike, can you transfer that back over to me? You're pretty adept at that. You're better than I am. Or maybe I can do it.
I think you have to request.
Yeah. Okay, sorry about that. Share my screen. Okay, so thank you very much. Okay, so in this next problem that you guys are going to be doing, number 15, it says the electric field midway between two equal but opposite point charges. So just in case you don't remember this problem, you can look it up online. Let's see if I can add it here really quickly so you guys can look at it. It's this problem right here. Okay, so I would suggest kind of drawing a picture. It says they're equal and opposite, so that means maybe one of them is positive and maybe the other one's negative or something like that. Equal magnitudes, so maybe they're both Q. This one's a positive one and the other one is a negative one, let's say. And you're trying to figure out what the magnitudes of those charges are, given that at a point midway in between, we know what the magnitude of the E field is. It's 586 newtons per coulomb. So the first thing I would do is kind of draw in what those vectors would look like from both 1 and from 2. And then to figure out if you're adding them or subtracting them, write your equation up, set it equal to 586, and then solve for charge. Keep in mind that Q, the magnitude, is the same as Q2. Any questions? Okay, why don't you go ahead and get back in your whiteboarding groups and do that one. How much more time do you guys need? Okay, I got one year ready. Is there anybody else? Any other groups? I don't want to make you go too fast. How about Natoli's group, Dvorak's group, Adams group, Atkins, Dury, Eli?
I am in Natoli's group.
Okay. What about some of these other names? How are you guys doing? Mark. Close, okay. That's there. Okay. Okay, Mark's still working. Keep on working then. Okay, rather not present, it's fine. How about Missy's group? We're done, okay. Again, if you guys need help or something, since I don't have your whiteboard URL, you know, you can always type in a chat that you need help or something, and I'll try to get over there and see if I can help a little bit. Okay, well, can I have anybody volunteer then? Any volunteers? A different volunteer. A different volunteer, sorry. Different group, I'm hoping. Okay, so let's see if I can pass it to Ben. Let's see, here we go. All right. Okay, perfect. So we can see your screen pretty well. Okay.
Can you guys hear me?
Yep, we can hear you.
All right, is that volume good?
Yep, perfect.
Okay. So, we knew that the midway point was, oh, whoops, let me change colors here. 8 centimeters away from both these charges, and they have equal but opposite point charges, and we knew that FE net. Oh wait, no. Wait. Oh shoot, I think we did this wrong.
No, I
Here,
think you got the right answer, don't you? That's what we got.
Yeah. Okay, never
Well, show us why that's the right answer by drawing your arrows in.
Because if you have a positive charge in the middle, then it's
Both will send
being
in the same direction.
pushed away by the negative and attracted by the positive, so you need to add them.
Okay, so no, wait a second. So
I mean,
you're
other
saying,
way.
okay, all right. So
Yeah.
there's going to be a vector toward the negative from the negative, and there's going to be another vector toward the negative from the positive, right?
Right.
Right, and that's why we add them together, and that's where you get the 2 at, right?
Yes. Yeah. So we can get the 2 basically because they're equal but opposite, so we know we have to add them. So then you just plug in your knowns. We have K. We don't know. We're solving for Q1. We know it's 0.08 squared, and that equals the 586 number. And then we just solved for Q and got this.
Perfect. Does anybody have any questions? Missy, I don't know how to make the text bigger. Michael was having the same problem, and I don't really know. If anybody has any ideas, that would be great. I'm going to go ahead and take... Say it again, Mike.
You mean the text on Twiddler? Like
Yeah,
that?
I think so. I think that's what she's talking about.
Okay, well, I mean, on the text tool, you could probably change it when you're in the typing mode.
Okay. Okay. Well, and there's a zoom on Join Me. I didn't know that. Okay. That's good to know. Okay, so I'm going to go ahead and take controls again. Thank you. Okay, so now what we're going to go back to the field comparison worksheet. And this one, I think what I want to do is kind of more of a lecture and have you guys chime in through the texting or if you want to say something if you have questions, okay? So the first one we're going to look at is, let's see. This one. This is just kind of sketching. On this worksheet, page 3, it has these graphs that I just want to kind of sketch in. Now, what I'm hoping that you remember is you guys had the thing with the tree, and you had to draw in the gravitational field for this. And if you remember, boy, this is a horrible job, but they were all straight downward, and you guys described them as uniform, and that's about as good as I can do. I'm hoping you guys remember that. Do you remember? Say yes or no or something. Okay, good. All right, so what's true about that field besides being uniform? How would I sketch that? I'm drawing the gravitational field versus the distance away, assuming this is an infinite plane. There's no relationship. Do we agree? Okay. Okay. All right. So it would look like this. No relationship. So then we also had a infinite line, or actually an infinite plane of negative charge. And you had to draw in the E field for this. And it kind of looked like this. And again, you guys described it as being uniform. So if I were drawing a graph for this, the E field versus the distance away, what would it look like? Slope of 0. Again, there's no relationship. Perfect. Stop me if you have questions. Okay, I think that one's a pretty easy one. Let's see if I can do another one here. The next one I want to go to that we talked about is the point mass. Okay, so here we have, so this was the Earth. We were really kind of far away. Do you remember the picture? I'm hoping you guys do. That was where we had the Earth like this, and you guys had to draw in the E field, or not the E field, but the G field around this. What kind of relationship was this? Inverse square. Inverse square? Was it inverse or inverse square? Inverse square? Okay, inverse square. Now, the truth is, when you look at an inverse square compared to an inverse, you're not really going to be able to discern the difference until you try to linearize it. But we do know this is an inverse square relationship, even though it looks like it's just regular inverse. Right? So, any questions about that one? Okay. Now I'm going to go ahead and skip one. I'm going to skip the infinite lines, and I'm also going to skip inside a uniform spherical mass. And I want to go to page 4, where it says inside a spherical shell of mass. Okay, so what I want you to imagine is, let's see how well I can draw this. Imagine that we have the Earth, and some strange aliens played a trick on us. This is actually a sphere that all the mass is the shell. In other words, if you could drill through the surface of the Earth, it would just be an empty space in the middle. Okay, so some strange alien things going on here. And let's say somebody did that. They were to drill through, and they actually jumped through here and they're, let's say, at this point in here. So maybe they're falling or whatever. Don't worry about the falling part. So just imagine them that they're there, okay? So I want you to think about the gravitational field on them, okay? Now, keep in mind that the mass over here on the top side that's really near them, that's going to exert a greater force on them, right? So there's going to be a force this way. There's going to be a force this way. There's going to be a force this way. But there's also mass on the far side that's going to be attracting them too. But how will that force compare to the force, the magnitude of it? How will the magnitude of that force compare to the ones I've already drawn? Less. That's right. Perfect. It's less in magnitude. But I want you to think about the mass that's on that side. Can you see that there's more mass on that side than the mass that's closest to them? So if I were to draw a dotted line through here, kind of right through the mass, let's see if I could do that. If I had to draw a dotted line through here, there's more mass underneath that dotted line than there is above it. So even though these vectors are smaller, there's more of them. A lot more of them. That one's too long. That one there I just drew is too long. Sorry about that. But there's a lot more of them. Do we agree with that? Because there's more mass? Okay. So my question to you is kind of a conceptual question. If I were going to add up all those vectors, what do you think it would be? How do you feel about that? Mark said it would be 0. What do you think? 0, right. What if I were to have the person not there, maybe right in the center? What would the net result of all those forces be? 0 again. What if it's over here somewhere? Again, keep in mind this is a spherical shell, and my drawing's horrible. It has to be nice symmetry here, nice and spherical. Can you see that it's 0 everywhere? Anybody have any questions about that? No. Okay, so I kind of thought you guys would get that one. So what we're saying is everywhere inside where R is less than big R, the radius of the Earth, in this case where it was a hollow Earth, there would be no gravitational field. And you'd just be floating in there, which is kind of cool. And then over here, what do you think it would be for for the electric field? So again, imagine that now we have a sphere that's made out of some conductor, kind of like the Van de Graaff that I have in the room. And it's actually a shell. What do you think the E field would be anywhere inside of that shell? 0. I'm hoping you guys see that there's a lot of symmetry here. Yeah, it's going to be 0 again. Any questions about that? Mark had a question, I missed it earlier. So would they continue to fall at a constant rate? Yes. Mark asked if they would continue to fall at a constant rate. Yes. So let's say they jump up in the air and they're going to be accelerating downward at 9.8 meters per second each second until they go through that shell. And then it's just a constant rate all the way through to the other side. Is that awesome or what? That'd be totally cool. Okay, so no. Okay, so I'm going to go on to the next one. I think I have a couple minutes left. And the one I want to do is actually back on page 3, and it's inside a uniform solid sphere. And this will be the last one I do, and I'm going to change you to do the line of mass yourself. Okay, so this one is saying, again, it's not exactly the Earth here, because the Earth is not uniform throughout. It gets more dense. That's a better sphere. As you get closer to the center, it gets more dense. Let's just say it's nice and uniform throughout, and you were to drill a hole all the way through, maybe. And we want to figure out what the gravitational field is all the way through. And again, this is going to be R is less than big R. I suppose you can even say r is less than or equal to big R, if you want to. So Missy's asking, you're cutting out what? Okay, wait a second. You're cutting out what? Oh, I'm sorry, Missy, you're saying I'm cutting out electronically. So I have this Earth here that I am drilling the hole right through. And it's not exactly the Earth. It's going to be some uniform solid sphere. So this one's a lot harder. What I want you to think about is what would the gravitational field be right at the center? Think of the last problem. You'd have mass over here that's pulling on you, mass over here it's pulling on you, mass everywhere it's pulling on you, but you're right at the center. So what would the gravitational field be? 0. Yeah, that one's easy, right? So it's 0 there. So in other words, if I could place you there at that point with 0 speed, you would actually just be floating there. And you wouldn't be able to go anywhere, okay? Now I want you to think about what's the gravitational field at the surface. And this would be like the surface of the Earth. So what's the gravitational field at the surface? It's G, right? It's some value. Yeah, it's going to be some value. Okay. Now, since this is uniform density, I want you to think what's going to happen to that gravitational field as we go out toward the surface. Can you see that it's going to be increasing? The question is, you know, how does it increase? Is it going to be a side opening parabola? Is it going to be a top opening parabola? Or will it be kind of direct relationship? What do you guys think? This is totally a guess, and I'm not going to prove it to you at this point anyway. All of them. Okay, so we're not really sure. The way this turns out, this is actually going to be a nice direct relationship as we move outward. It's going to be linear as you move outward. And I will prove it later on to you. So anyway, my question is, what if we had a spherical conductor? So this is a ball of metal, and we did the same thing. What do you think the E field would be as you move outward? It'd be linear as well. Yeah, it's going to be like this. So I think I've already used all my time up as I promised. I think probably more than that. So what you've done, we've done everything that I want to do on page 3. I don't really want to do any more page 4 because it's pretty tough. I want to do that together. I want you to kind of think logically on page 3. There's one we haven't done, and that's the infinite line of mass, and I'm sure Kurt will really enjoy that one. Your hint is this. Look at the first one. Remember we said that's constant. The next one, the point mass, we said that's an inverse square. Then the bottom one, we said that's linear. We said that's 0. There's something we're missing there. Maybe you can figure out one line, okay? That's it, though. No, nothing else. Any questions? Okay, that's Ben. Sorry about that. I hope somebody can kind of email Ben and kind of give him the hint. So you can work on your internet homework, finish up the lab response. It'll be due tomorrow. Okay? So the hint again was, just in case your audio just came back on, is look at what the relationships are. The very first one was constant. The next one's inverse square on page 3. Then the last one on that page is a direct relationship. And then on page 4, at the top, we have 0. So kind of think about the one that's missing. Okay, so again, thanks for joining us, and hopefully see you guys tomorrow. Okay, so sign off. Okay, bye. Thanks again.